So now let's talk about regression assumptions. So here's where we are in steps in data analysis. We've thought about our files, we've collected the data, thought about a research question, and checked it against the requirements. Okay, we have more requirements that we need to check against, and those are the assumptions. So here's that whole assumptions section, which probably didn't make any sense when you see it, but now we're going to actually go into why it's important. So the reason that we run descriptives to start out with is really to take a look at our data and make sure it's appropriate for regression. So in that case, we need to check for violation of regression assumptions. So when our data doesn't meet these assumptions, that's called a violation. Regression has 4 assumptions that we need to check for. And we can check for these at 2 points: before we run the regression and after we run the regression. Most of these assumptions are going to have to do with the error terms, right? And remember that error is just the actual value minus the predicted value. In this context, we also sometimes call our error residual because they're left over after you predict the value. So we can check the residuals after the regression, but by looking at the distributions of the variables and their relationships before the regression, we can actually see a lot of these issues that might happen before we even have to get to that stage. So these are the 4 regression assumptions: linearity, independence, normality, and equal variance, or line. So in general, when we are violating our assumptions, these are some of the things that can happen. When we run a regression, we get what we're calling parameter estimates, right? These are about the relationships between our variables that are in the population. We're just using our sample to estimate to the population. So we get our estimates, but we also are using hypothesis tests to determine the statistical significance of our estimates. So if we are violating the assumptions of regression, then our estimates to start out with are going to be biased. The numbers are misleading and they're not giving us the best value for what we're trying to estimate. It's just not a match. But our hypothesis test might also end up being inaccurate in that we don't know if that estimate that we got is statistically significant or not. We're just not able to get enough precision there. So those are general consequences, and then for each assumption, I'll tell you about the more specific consequences. In terms of severity, violating linearity is the most terrible assumption to violate, followed by independence and then equal variance. And normality, it's actually pretty okay to violate that. All right, so here's a summary of how to check for assumptions before we run the regression. This is organized over here by what plot we look at, and then over here by what assumption you're checking for. So we'll go through this by assumption first, and then we'll look for the plots. All right, so the first assumption is linearity. Linearity says that the relationship between the outcome variable and the predictors is accurately described by the linear model equation. That there's a line, basically. This is the worst assumption to violate, but also the easiest to fix. So the consequence of, say, trying to model a straight line here, when this data is very clearly a curve, is that our model is going to be inaccurate, right? There's not really very much point estimating a line that goes more like this than it actually fits with the data. It's not going to fit. Our estimates and our hypothesis tests are not going to be useful. But fortunately, we can check for that by running a scatter plot between our x and y variables before we run the regression. So here's some other examples of what nonlinear data looks like, right? So here you can see we've drawn a straight line, and it actually goes through some of the points, but you can see this curve right here would probably be a better fit to the data. And here where you can see that they've actually fitted a curve to this data, and you can see how it's much closer to a lot more of the dots than if we just drawn a straight line going down that way. So fortunately, it is possible to use an equation to model a curve like that. We won't get into that in this class, but it is possible. So if you see this kind of curve data, then you know you need to use a curvilinear regression instead of just a linear regression. So our next assumption is independence that we're going to talk about, and there are 3 types of independence. The independence assumption itself is that the error terms, residuals, are statistically independent. So one error term is not giving any information about another error term, right? And there's 3 ways that we can violate this. We're going to talk about correlated observations and correlated predictors right now, and then we'll talk about missing variables once we get to after the regression. So the first problem in terms of lack of independence means that could be that our observations are correlated. Basically what this means is that observations are cases that happen after another one might be giving some information about the ones that come before it, or are more or less likely to have certain characteristics because of the ones that come before it. So if you look at this line over here, what you can see is that these observations go up for a certain point, and then they start going down again, right? So if you were looking at this observation right here, you would probably be able to guess that it would be lower down here because it's coming after these higher values. So these observations are connected in some ways. An example of this that my student from last semester actually gave me is that if you look at turtles basking in the sun, then you see data that looks like this, right? Because the turtles, they're reptiles, so they're cold-blooded. They will go out into the sun, their temperature will rise, and then they get cold, they get too hot, so they go back. And then when they get cold again, they go back out into the sun, get some heat, and then go back in, right? So the turtles' movements are not completely independent of each other. It's not just wandering around randomly. It's going in and out of the sun because it wants to get warm or to regulate its temperature. So some other examples of the way that observations can be correlated is if you have students who are nested within classrooms, or if you have states that are nested within regions, right? Any kind of observations that are connected to each other through some broader structure can be give you information about each other, right? So if you're a student in the classroom, then the fact that you have the same math teacher as another student could mean something if you're trying to predict that student's math grades, right? So how do you check for this? You really need to know your data, know where it's coming from, know how many people are connected to each other, how many cases might be connected to each other. You can look at it on scatter plots like this, and you can also run a statistic that we call the intra-class correlation, which we're not going to talk about, but if you do have data that's nested within classrooms or something like that, then that might be something you would look into. So what are the consequences of violating independence? Our hypothesis tests are going to be inaccurate. Your estimates are going to be fine, but you're not necessarily going to know whether or not your data is statistically significant. The remedy is really to use another form of regression, which we'll talk about at the very end of the class. So a second way to violate independence is to have correlated predictors, and this is called multicollinearity. So some way to look for this before you run the regression is just to look at correlations, or to look at t-tests and ANOVA and see if something is, two variables are very highly predicting each other, right? So if you have correlations of 0.8, 0.9, that's usually could be a problem for your regression. If you have grouping variables where almost everyone is in one group and no one's in another group, that can also really be a problem. The consequences are that your hypothesis tests are more likely to be non-significant, right? And you're not going to be able to determine the relative importance of different independent variables, right? So if you're doing an analysis where you're looking at gender and homework, how much time you spend on homework on your math grade, but in this particular sample, almost all of the boys have a poor math grade, then that boy variable is going to take over so much of the variance, and you're not going to be able to see how much homework time is really playing a role. Right? So how do you fix this? Well, you might want to use only the most important variables. If so many of the boys have a poor math grade and you really want to look at homework time, then maybe you just need to do your analysis in the boys only and leave out the girls. You can also run separate regressions, right? So you can do a regression looking at homework in the boys and in the girls. If you have correlated quantitative predictors, continuous predictors, then you can also run separate regressions using just the predictors that in one that's not, the two predictors are really correlated with each other, so you want to run a regression with one of them and another regression with the other. Not perfect, but it can work. So that's the independence. So remember I talked about there's going to be 3 types of independence that we look for to be violated. We'll talk about missing variables after we learn about residual analysis. And so then our next assumption is normality, which is that the errors are normally distributed. Pretty easy, right? So how do we look for this? Skewness and kurtosis again, right? So we can look at this at our independent variables, our dependent variables, and then after the regression, we can look at our residuals. So just to remember, here's skewness and kurtosis, right? So skewness is how much it leans to one side or the other. Kurtosis is how flat or skinny it is. So the more these numbers are off, the less normal your data is. Another thing you're looking for when you're looking for normality is outliers, or what's called influential cases, right? So this is the idea that in your independent variables, your dependent variables, or your error terms, your residuals that you look at afterward, you're trying to see, are there any cases that are just kind of out and might be disrupting the data some? So let me give you some examples of this. So here's a histogram where there's an outlier over here at 20. Everyone else is pretty much bunched over here, but they're over here. So this doesn't actually disrupt the normality of the data so much, but it does mean that it could, you might be trying to estimate something for a bunch of people who don't exist in this middle portion right here. When you take out that outlier, you can see that the spread of the data is actually, not too bad. It's just that it's a lot narrower than if you were including that influential case, that outlier. In a scatter plot, we can also have issues with our outliers where they might pull the line up more or down more than they should. Right, so this is the same data with these outliers here and without the outliers. And notice when we have these outliers up here, this line is wanting to be pulled up really sharply, and the line is less connected to all of these points because it has to try and get up to those points. But if we take those outliers out, the line's fitting much better with a lot of our points. So as you can see, some of the consequences of lack of normality or having outliers could be that we're not getting the best fit for our line. Our hypothesis test might be inaccurate. But in general, normality is not a huge problem because if our sample size is large enough, then all that stuff about normal theory that you learned about in Quant 1 is still going to apply. So we generally don't worry too much about lack of normality unless our sample is really small. And I'm talking like, 30 or something like that. So what can you do to fix problems with normality or outliers? Check for errors in your data entry, right? So if you saw this 20 over here and your scale only went up to a 5, you'd probably want to say, okay, someone misentered that. You can do transformations. So in some of your textbooks, you can see how to do transformations to make your data more normal. If you have outliers, you can remove them, and you can also use what's called robust methods, which we won't get into, but there are definitely ways to use to run regressions that relax this assumption quite a bit. So our last assumption is the equal variance assumption, and this is the one with the most fun names. We call this homoscedasticity or homogeneity of variance. So this is basically that the variance or the spread in the dependent variable is similar across all levels of the predictors. And the best way to talk about this assumption is really just to show you a picture. All right, so here's a scatter plot of income and age. And what we're looking for is the spread to be similar across the entire point here, plot here, right? But you can see, obviously, the income that people earn when they're 15 or so is going to be pretty low, but it's also a lot less variable than the income that people earn when they're in their 40s, right? When you're in your 40s, you got some people who are unemployed down here, you got some people who are earning just kind of a normal everyday job, but you've also got your CEOs up here who are earning a ton, right? So the spread is much wider here than it is down here. What we would say is the variance is not constant across age, right? So you can see this in scatter plots of your independent variables and your dependent variables. Once we get after the regression, you'll be able to see it in your residual plots. So what are the consequences of this? Yeah, optimal, your parameter estimates are not going to be optimal, but they're not going to be biased either. So, it's not the best, but, it's going to be okay. The real problem is going to be with your hypothesis test, and that you might be getting inconsistent results than if your variance was more standard. So what are some remedies to fix with this problem? You can use those robust methods that we're not going to talk about. You can restrict the range, right? So instead of saying, well, let's look at everyone's income from age 15 to 45, why don't we just say, let's look at the older adults' income. So we'll start at age, 30 something, and just look at the relationship between age and income in that group of people. Right? So there are some problems that could come with that. One is that you're kind of artificially limiting your sample. Why is 30 a good age and not 15, right? But at the same time, you might have less problems trying to fit a regression to this data. And then the other is to change your variables. So is age really the most important thing you're looking for when you're thinking about income, or could you use years of experience instead? That might have less of a problem with this sort of unequal variance. So that's the equal variance assumption. So here's how you check for these assumptions before the regression by particular plot. So when you look at your histograms, you're going to check for normality, right? Do you have a nice smooth bell curve? Do you have outliers somewhere? When you're looking at scatter plots, you can see outliers. You can also look for linearity. So is there a straight line here? Is there more of a curve? You'll be able to check for independence in some cases, especially if you're looking at time or some variables that show you the connection between people or cases. And you can look for that equal variance assumption here. So here's another case of where the data kind of funnels out as you get more toward the right side of the plot. And even when you're looking at your box plots, you'll still be able to tell, are there outliers? The box plots specifically point out outliers to you. How much of a problem are they? Independence, right? If you're looking at a categorical variable, you'd want to see how much is your Y value being predicted by what group people belong to. And you can see equal variance by looking at the relative size of these bars here. Right, so you can see in this group, they're a bit more spread out than in these two groups. And you have to determine how much that's a problem. So how much are all these things a problem? The issue with assumptions is that in general, they can create bias and make your hypothesis test inaccurate. But there's not going to be any very strict cutoff point for when something is violating an assumption. It's a lot of judgment calls, and it's a lot of balancing what kind of data do you have, right? What questions did you ask if you're doing a survey? Can you go back and get better data? How new is the research question? How severe is the violation? Are there other assumptions that you're going to violate if you try and fix this one violation, right? So there's a lot of things to take into account. So there's never going to be a very clear okay, this data violates this assumption and it can't be used. So that's just to say, prepare for ambiguity when you're checking for assumptions, but it's definitely something that you should do, and it's really important to think about with your data.